the autoionization of water. In this video, you will learn how to calculate pH for very dilute quantities of acids where the autoionization of water cannot be assumed to be 0. In all these calculations that we've been doing with weak acids and weak bases and strong bases, it's important to think about, well, have we been ignoring anything, any species? And here I would question, is the concentration of H plus or OH minus really 0 initially? If we think back to the early introductory parts of this chapter, we stated that water ionizes to a small degree. Let's remind ourselves to what degree, by putting it in the context of things that many other people tend to know from earlier science classes. The pH of neutral water at 25 degrees Celsius is 7. What does that mean about the H plus and OH minus concentrations? They must both be about 10 to the negative 7th, depending on the exact temperature. But that isn't 0. So why do we start our ice charts at 0? Was that wrong? Does it matter? In all our calculations, we've been ignoring that this equilibrium is occurring. And if you look at the Kw, or the K for water, you can see it's very small. Since it's very small, we can generally ignore it, but not always. If the H plus or OH minus concentration is around 10 to the negative 6th or smaller, you need to account for this. Because you may be saying, well, look, it's a small number. I don't believe her. Let's do a calculation to prove it. We'll do a simple strong acid calculation without considering the autoionization of water. We'll fill in the value for H plus into the negative log of H plus to get the pH, and it comes out to be 8. Does this make sense? We added acid to water, and we ended up with a basic solution. That definitely doesn't make sense. Let's see how we can do this in a way that gives us a correct answer. We're actually going to start out with a weak acid calculation and come back to this one later. That's because a weak acid calculation is done very, very similar to how we did them before, and so it's just one additional step to add in. We'll have to change our protocol for doing a strong acid, so we'll save that one for later. We'll go back to our formic acid example. Now for our initial values, instead of putting in 0, we'll put in 10 to the negative 7th. From here, everything else is basically the same. We'll add in our unknowns. The reaction must shift to the right since there's no anion present. And then fill in our equilibrium line. From here, we can fill into our Ka equation. Note, however, that none of our assumptions can be made. We must leave all the x's into our Ka equation. Now that we have our equation, we can solve for x using the quadratic formula and fill into the ice chart. I'll leave it to you to do the algebra. Then using the equation for pH, solve for pH, just as we did before. Now let's go backwards a bit to our original problem that we used to show that this assumption isn't always valid. Because we are now dealing with the equilibrium of H plus and OH minus making a difference, we must do an ice table using the equation for water and Kw to decide how much of the water will dissociate given the concentration of the acid. From here, it is very similar to a weak acid or base problem. So let's fill in our values. We had 10 to the negative 8th from our solution of HCl, 0 for our OH minus, and we'll now see how much the water will dissociate given this value. We use the equilibrium formulas to fill into Kw, which then allows us to solve for x. By filling into the ice chart and into the equation for pH, we can solve for pH. This answer makes much more sense since it is below 7, but not by too much. In this video, we have now learned how to calculate pH for dilute quantities of acids where the autoionization of water cannot be assumed to be 0.